Assalamu alaikum. Welcome back. It is said that wise people learn from other people's mistakes, whereas fools don't, even from their own mistakes. So in this lecture, our aim is not to be fooled and not to fool when we're doing NPE studies. So we're going to study some common errors that people make when doing network performance evaluation studies. And we're also going to study some logical fallacies, which is error in reasoning. And we're also going to study some cognitive biases which make us prejudiced towards making logical errors or other reasoning errors. So let us start by talking about logical fallacies. Logical fallacies can be classified into two broad categories. The first one would be fallacies of evidence, and the other one would be fallacy of relevance. So before we understand what fallacy is, we need to understand what is a non sequitur. So a non sequitur is a logical argument in which the conclusion we're making does not follow from the premises. और ये इसको हम math reasoning error भी कह सकते हैं, logic का error भी कह सकते हैं. And there are other informal logical fallacies as well. So we are going to cover both. So we start with fallacies of evidence. We define a fallacy of evidence as an argument which has a non sequitur of evidence. So let me give you an example. As we've mentioned before, when we're talking of logical arguments, we can divorce the content from the form of the argument, and we can just analyze the form of the argument. If the form of argument is such that if the premises are true, the conclusion must necessarily follow, we call this argument a valid argument. And if we have a fallacious argument in which the conclusion does not follow from the premises, we call this a logical fallacy. So let us consider some formal fallacies of evidence. So the first example would be, if A, then B, C, therefore B. So the first premise here is that if A happens, then B would necessarily happen. The second premise is C has happened. But the conclusion drawn here, which is B, does not follow from the premise. So we say that this is a fallacy. या इसको हम आम फहम ज़ुबान में कहेंगे कि ये faulty reasoning है. Another example of a formal fallacy of evidence would be, if A, then B, A, therefore C. So if we analyze the first premise, which says that if A has happened, then B would happen. The second premise is that A has happened. But the conclusion that C would happen does not necessarily follow from the two premises. So these are examples of formal logical errors of evidence. And there are many other examples. इसके अलावा there is an entire field, an entire category in which you have informal fallacies of evidence. And we're going to take a look at some of them. So by necessity, we are only going to scratch at the surface of the field of fallacies. There are so many fallacies that we cannot possibly cover them all. But the idea is to expose you to some important fallacies, and I expect that you would go and read more about this. So I'll give you some informal fallacies of evidence. The first one is hasty generalization. And hasty generalization is an inductive fallacy. I hope you remember that when we talked of science, we said that science requires both inductive and deductive reasoning. Deductive reasoning में हम ऐसे करते हैं कि we assume certain axioms, and then we say if we assume this is true, what must necessarily follow. लेकिन जब हम induction की बात करते हैं तो हम कुछ observations लेते हैं और उसको generalize करते हैं into a theorem or a hypothesis or a law, and we say that if this hypothesis is true, what must then also be true. उसके लिए फिर हम experiments करते हैं. तो ये जो induction का process है, इसमें अगर हम fallacy करें, for example हम एक observation से एक broad hypothesis बना लें, then this would be the fallacy of hasty generalization. Let us consider a dialogue between a wife and a husband. Wife: I'm giving up extreme sports now that I have children. I think I will take up golf. Man: I wouldn't do that. Do you remember Iqbal? He was playing golf when he got hit by a golf cart. It broke his leg, giving him a concussion. He was in hospital for a week and still walks with a limp. I would stick to paragliding. So if you see this dialogue, you would see that the man is generalizing from a single evidence. And we call such an evidence anecdotal evidence. Anecdotal evidence का मतलब है कि एक particular story से हम अपनी broad generalization बना रहे हैं. Anecdotal evidence यहाँ होगा कि इस example में Iqbal got hit by a golf cart, he had concussion, he had all this sad story. So because of that, the man is generalizing that paragliding is a more safer sport than golf, which is obviously false. So this would be an example of hasty generalization, and this is an example of an inductive fallacy. The tendency to generalize hastily actually follows from human psychology. Humans generally like stories and anecdotes, and they tend to form conclusions based on these stories and anecdotes. But when we're talking of science and we're talking of doing a formal study of network performance evaluation, we cannot simply rely on stories and anecdotes. So to remember this, it would serve us well to remember the quote that the plural of anecdotes is not fact. So let me give you another example. 6 Arab fundamentalists were convicted of bombing the World Trade Center in New York City. The message is clear. Arabs are nothing but a pack of religious fanatics prone to violence. So we see the same fallacy here. A generalization is made based on a very small sample, and this small sample only consists of 6 men, and a very sweeping generalization is made that all Arabs are religious fanatics and they're prone to violence. So we must take care that we do not generalize hastily from a very small sample. In fact, when we talk of sampling, we'd be seeing that the science of statistics actually tells us that how confident we should be in an inference that is made from a sample. So if we are estimating from a small sample, the variance in our inference would be large. Or we actually call this standard error, which means when we are making an inference from a sample, we would not be very confident if the sample size is small. So when we talk of polls, and you would know a lot of examples of polls, they are very common in newspapers. When we see that, for example, Gallup poll has made a poll regarding this. They have asked this question to a sample of maybe 1,500 people, and they have replied in this manner. But they also state that, this conclusion is uncertain in this range. So they would also state their range of uncertainty. For example, they would say that our poll is predicting that candidate A would win this election with a percentage of 65, but also they specify the range that our estimate may be off from the true value by, let's say, plus minus 5%. So hasty generalization is specific to induction and the scientific process. So it is very important that we understand this and we avoid this in our evaluation studies. Let's look at the next fallacy. The next fallacy is known as questionable cause, in which we are establishing a causal connection where no such causal connection is warranted. So there are 2 specific cases here. The first one is known by the Latin name post hoc ergo propter hoc, which means after this, therefore because of this. So if something happens in a particular sequence, people tend to automatically think that the thing which is following was caused by something which happened before it. But just this order of happening does not actually give evidence that the first thing is the cause of the second thing. When we talk of a causal connection, we actually mean that whenever the first thing happens or whenever the cause is there, the effect is inevitable. But when we are dealing with this fallacy, oftentimes it's just a chance occurrence. For example, let me give you an example of this. When the fuel light goes on in my car, I soon run out of gas. Therefore, the fuel light causes my car to run out of gas. So in this case, two things are happening one after another. Once the fuel light goes on, after some time the gas would run out. So you would always have this sequence. But the light turning on is not actually causing the gas to go out. It's the tank becoming empty of gas. So that's the confounding variable or the real cause. And we are observing two variables that seem to be correlated. And in this case, one is following the other. So we tend to form a causal opinion of this, that the first thing is causing the second thing, but that may not necessarily be true. So this is one specific case of questionable cause, which is called post hoc ergo propter hoc. Another category of fallacy which falls under questionable cause is called cum hoc ergo propter hoc, which means with this, therefore because of this. So this actually is also stated in old adage which says that correlation is not causation. If two things are correlated to each other such that, if one thing is increased, the other thing is increased as well, this does not necessarily mean that there is a causal connection. So let me give an example. Dogs bark before earthquakes. Therefore, dogs can sense that an earthquake is coming. So in this case, just because a dog barks before an earthquake does not necessarily mean that a dog can predict an earthquake. These two may be just coincidences. So we have to be very careful that we do not mistake correlation for causation. Especially because in this case, dogs bark even before earthquakes, they bark during earthquakes, they bark even after earthquakes. So it would be clearly fallacious reasoning if we mistake this correlation, that dogs bark before earthquake, for causation. So this was actually a caricature of a fallacious argument. Actual arguments are going to be more subtle than this. And, people would therefore fall for this trap of, thinking that correlation is causation. But whenever we are making inferences about causation, we have to do it through, properly designed experiments. Just by observing the correlation between two variables, we cannot make any causal inferences. And we'll be talking about this when we get into the section of statistics. So let me give you another example of a fallacy of evidence. This fallacy is called Texas sharpshooter fallacy. और इसका नाम Texas sharpshooter fallacy क्यों है? So it is because of a story in which a man in Texas, he claimed to be a sharpshooter, और एक side पे fence पे he started shooting with a rifle. And after he shot many shots, उसके बाद उसने जाके जहाँ cluster बना हुआ था उसके इर्द गिर्द उसने निशान बना दिया. And afterwards he started saying that look at this, my shooting is so precise. This kind of fallacious reasoning is often done in arguments. And many times in observational studies, people sense some patterns in data, and then they, from there form hypothesis and present the data itself as evidence of that hypothesis. So we must understand कि जिस data से आप hypothesis बना रहे हैं, उसी पे उसको test नहीं कर सकते. उसके बाद आपको दोबारा properly designed experiment करना पड़ेगा, in which you're trying to falsify your hypothesis. So as an example of this, so let us consider firstly what people have defined to be a miracle. So many people have thought about what constitutes a miracle, and they say that if something has a chance of 1 in a million, then we can call this a miracle. To illustrate the Texas sharpshooter fallacy, let us consider an example in which we flip a coin 20 times. And let's say we get a sequence heads, tails, heads, 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 tails, heads, tails, tails, heads, and so on, as you can see in your slide. This is, pretty innocent looking. But if you claim that afterwards, after getting this particular strings of heads and tails, if you calculate what is the chance of exactly this string coming up, the chance is 1 in a million. Because if you see, there are 20 flips of the coin, and on each flip the chances are 1 in a 2. So half probability of a heads and a half probability of tails. So if we flip the coin enough times, उसके बाद जो exact string आया है, that's very improbable. In fact, if you were to predict this before flipping the coin, you would be very hard pressed to do it, because it's very difficult to predict this before throwing of the coin. तो अगर हम इसको observe करके कहें और देखें कि कहें कि देखें इस particular string के आने की probability इतनी कम है, इस वजह से this is a miracle, then this is clearly fallacious reasoning, because you did not have this information before you flip the coin. उसके बाद जब experiment हो जाए, you can always find a pattern which would be very improbable. इसी तरह in many other scientific studies, people find particular patterns and then they retroactively reason that what are the chances of this happening. So whenever we are making such reasoning, we should actually be making a hypothesis and then testing it out with another experiment. Texas sharpshooter fallacy वहाँ apply नहीं होता जब आपके पास ये hypothesis पहले exist करती है before the experiment. So if, for example, you had this information कि exactly यही string आएगा, so that would not be Texas sharpshooter fallacy. But it is precisely the reason that you're reasoning from the results that you've observed after the experiment that this is called the Texas sharpshooter fallacy. So as a last example of an informal fallacy of evidence, let me give you another category which is known as appeal to ignorance. And in this fallacy of evidence, we actually say that because no one has disproved this claim, then this claim must be true. Or this claim must be false because no one has yet proved it. So in both these cases, we're appealing to ignorance for evidence. And in scientific arguments, such an evidence would not work. So as an example of the appeal to ignorance fallacy, let us study an example. So no one has ever been able to prove that UFOs don't exist. Therefore, UFOs do exist. Or another example, to study user satisfaction with a software product, we sent out 5,000 questionnaires to registered users. Only 100 users filled out and mailed back their questionnaires. Since more than 4,900 of the 5,000 users did not complain, the vast majority of users are satisfied with the software. So in this case, no evidence of dissatisfaction is not evidence for satisfaction. So we must be very careful using such arguments. So having talked of fallacies of evidence, let us now change our topic to a fallacy of another kind, which is fallacy of relevance. Or fallacy of relevance may be, there are two types, formal fallacies और informal fallacies. जो formal fallacies होंगी उनकी सिर्फ हम argument की form देख के हम कह सकेंगे कि this is a fallacious argument. But for informal fallacies, we have to observe the content. So let me give you examples of both. Initially, we start with formal fallacies of relevance. So if A, then B. This is the first premise. The second premise is B. Therefore, A. लेकिन दोनों premise से it does not follow that A would happen. In fact, B का होना irrelevant है, and we cannot conclude that A would occur because our initial premise only states that if A has happened, then B would happen. As another example of a formal fallacy of relevance, if A, then B, not A, therefore not B. Again, this does not follow. इसको हम कहेंगे this is a non sequitur of relevance. ये दोनों जो examples थे, ये examples of formal fallacies थे. अब हम informal fallacies of relevance की बात करेंगे. So the first example we're going to consider of an informal fallacy of relevance is an ad hominem attack, which means that instead of countering the argument itself, you actually start insulting the person who made the argument, and from that you conclude that, okay, if this person is so bad, we cannot believe anything he says. As an example, Iqbal claims that we need to upgrade our router's RAM to improve network's performance. He is just a fresh graduate who barely passed his college exam. Clearly he is incompetent. Therefore, we don't need to upgrade our router's RAM. So in this case, the evidence that we don't need to upgrade our router's RAM is based on an irrelevant premise. Yes, ko hum kahenge ki this is an irrelevant evidence that just because someone is incompetent according to you, it does not mean that all his arguments would be invalid. So we cannot simply attack the person making the argument and because of that disprove the validity of an argument made. And this is very common in political discourse. So we must understand this, that in logical arguments, it's not the person making the argument, but it's the argument itself. So you must address कि अगर premises true हैं, तो क्या जो conclusion है उससे follow कर रही है? अगर if that is the case, it does not matter who is making the argument. The form of the argument is what matters. So we must be careful to avoid this fallacy. And again, attacking the person making the argument is no proof of the way you want the argument to go. So another example of an informal fallacy of relevance is the bandwagon argument, which is also known as in Latin as ad populum, which means that you are claiming that because something is so popular that it must be right. So this is again logically this does not follow. अगर कोई चीज़ बहुत popular भी है, it may be that that thing is not correct, but still it is popular. So logic में popularity is no evidence for validity. So अगर कोई claim करता है कि because something is popular, ये claim जो है ये irrelevant है. As an example, millions of people share copyrighted MP3 files and videos online. Therefore, sharing copyrighted music and videos is fine. Just because millions of people are doing this thing does not make it right. So we have to be very careful. This is not a logical argument. Isi tarah, because science is based on logical reasoning, we cannot make such arguments in science. As another example, all over the world, copper cables are used much more than optical fiber cables. Clearly, copper cables have better transmission properties. Again, in this case, we have to observe that what is the conclusion? And the conclusion here is that copper cables are better than optical fiber cables. और इसके लिए evidence क्या present किया गया है? कि just because copper cable is more popular या ज़्यादा deployed है, it must be the better technology. It does not follow. And the premise is actually irrelevant to the conclusion. So we cannot make such a conclusion based on the premises that we have here. Another example of informal fallacy of relevance is what is known as a red herring. Again, this is very popular in political discourse. So, the fallacies we are learning here are general. They don't just apply to network performance evaluation, but they apply to, general life. So you can make use of these fallacies to understand when someone is telling you an invalid argument. So when someone uses the red herring technique, they're actually disproving some argument, or they are proving something by providing a distracting argument. So this would be clarified when we see an example. So this is again a political example that was used much, that I know there is no direct evidence of weapons of mass destruction, but he has gassed his own people in the past. We've got to take him out before he uses his weapons of mass destruction on us. So in this case, what is the first premise? In fact, they are saying that, the maker of this argument, that they have no direct evidence that the politician in question has weapons of mass destruction. Lekin dusra premise kya hai? Again, if you note carefully, this is an irrelevant premise. This premise is that he has gassed his own people in the past. Even if he has, it does not prove that he has weapons of mass destruction. और इस अगर आप आर्ग्यूमेंट में देखें कंक्लूजन क्या ड्रॉ की जा रही है, it is that we've got to take him out before he uses his weapons of mass destruction on us. So in the conclusion, implicit conclusion क्या है कि he has weapons of mass destruction. तो in fact अगर आप इसको नोट करें, इसमें रेड हेरिंग भी है because the second premise is actually a distracting argument. ये एक distracting argument है कि उसने और क्या past में किया हुआ है. The main issue now is, does he have weapons of mass destruction? And if you observe, जो conclusion है, it is actually contradicting one of the premise. So this may be actually suffering from multiple fallacies. As another example, there's another kind of informal fallacy of relevance which is known as a straw man. Straw man may, because you cannot beat some person, you replace him with a weaker person known as a straw man, and then you beat him and you claim that because I've beaten the straw man, I've beaten the original person. तो इसका जो argument का analog ये होगा कि original argument काफी strong है. You cannot defeat it, so you replace it with a weaker argument. And then you disprove that and you say that, okay, I have disproved the original argument. So again, let's see an example and that would clarify what this fallacy is about. Wife, we should clean out the closets. They are getting a bit messy. Man, why? We just went through these closets 3 months ago. Wife, you just want to keep all your junk forever, which is just ridiculous. So in this case, the wife's argument was that the closet should be cleaned because presumably a lot of time has happened before the last time closet was cleaned. But the man replaced this premise or this argument with a straw man argument, and he said that, why should we be cleaning these closets every day, and we just went through these closets just a while ago. So it is not addressing the real argument, but is replacing it with a weaker argument, and then by countering that argument, it is disproving the original argument. So in a logical sense, such reasoning is considered fallacious and is not considered acceptable. So this wraps up our discussion on logical fallacies, and we discussed both formal logical fallacies and informal logical fallacies, and we said that logical fallacies can be broadly classified into fallacies of evidence and fallacies of relevance. By learning about these fallacies, it is hoped that we will not commit these same mistakes and we will not fall for these mistakes. Now I would like to talk about cognitive biases. And what are cognitive biases? Cognitive biases are prejudices in human mind which forces them to do false logical reasoning. So this is a very active area of research in which many people have researched the human judgment in decision making, and they've seen many quirks. और बहुत सारी चीज़ें उन्होंने observe की हैं कि which is clearly not rational. So we are going to study some of these, and we are going to borrow from the research of two very prominent psychologists, Daniel Kahneman and Amos Tversky. और हम कुछ देखेंगे कि उन्होंने जो cognitive biases describe किए हैं, और हम देखेंगे कि in the light of these cognitive biases, logical fallacies would automatically result. So the first cognitive bias that we're going to talk about is the base rate neglect. Psychologists have shown that humans are not very good at probability. यानी कि human intuition जो है, it does not match with proper probabilistic reasoning. उसकी एक example है base rate neglect. तो इसके example हम study करते हैं, and with this it would clarify what this problem is. So base rate neglect में होता ये है कि you ignore prior probabilities when making decisions in light of new evidence. तो इसका एक example हम study करते हैं. If a person has cancer, the probability is 90% that he will have a positive test indicating cancer. If that person does not have cancer, the probability is 10% that he will still have a positive test. Now the question is that a person, he went for a cancer test और उसका जो result आया वो positive है. And in the light of the data given above, the question is, what is the actual probability that person has cancer? So apparently we have quite a grim situation here. The chances of test coming positive when someone has cancer is 90%, whereas the chances of a false negative, that is the person has cancer but the test comes negative, is only 10%. In the other case, when the person does not have cancer, 90% of the time prediction sahi hogi, but 10% of the time you would have a false positive. So in this case, naively, we would think that the person has around 90% chance of having a cancer. But we're going to show that a very important data is missing from the data that we already have. And that is, what is the prior probability of a person having cancer in this population. So if we are given that the base probability that any random person has cancer is 1%, how does this transform our question? So this actually indicates the fallacy, because many people would still believe that the chances of having cancer is around 90%, but we would show that the actual chances of having cancer is much less. So this actually follows from this, that when new evidence is presented, people often ignore the prior probability and they calculate the posterior probability just on the basis of evidence. Whereas the normative model, which is how things should be done, is that you should take both of them and balance them and see what was the prior evidence, what is the new evidence, and then form the posterior probability. So to indicate the fact that the actual probability is going to be much, much less than 90%, let us have a look at this animation. So suppose we have a population of 1,000 people. Agar is population mein we already know that only 1% people would actually have cancer. तो उसमें अगर हम 1,000 people में से calculate करें, only 10 people would actually be having cancer. और इन 10 लोगों में, if we actually conduct a test, only 9 of them would have a positive test, because the percentage of correct testing is 90%. You would have one false negative. One person would be having cancer, but the test will not be able to correctly predict it. In the other case, you have 990 people who do not have cancer. लेकिन इस केस में भी अगर हम देखें तो 90% चांस था कि टेस्ट करेक्ट रिजल्ट देगा, लेकिन in 10% of the case you would have a false positive. तो अगर हम, because there was a larger population who did not have cancer, इसमें से अगर हम 10% निकालें तो 99 out of these 990 people would have a positive test. So in all now you have 108 people who have positive test, जिनमें से सिर्फ 9 लोगों का असल में उनको कैंसर होगा. For the remaining people, for the remaining 99 people, they don't have cancer, but they have a positive test. So अगर हम इससे अब probability निकालें तो जिन लोगों को कैंसर है divided by all the people who have positive test, so this actually comes to be close to 8% and not 90%. So this is something very important. So conditional probability is something that many people have problems with, but if you see, it has much practical significance as well. So you may have a relative who got a positive test result, but you can use the laws of conditional probability. If you know that an illness is very rare, the chances are that even if someone has such a positive result, they may still not be having the illness. As a second example of a cognitive bias, we're going to talk of the so-called law of small numbers. In statistics, we have a valid law which is called the law of large numbers, and it is the basis of probability. When we talk of probability, that probability actually is in terms of long-term averages, and that's the beauty of probability. If we are going to toss a coin now, we do not know if it's going to come a heads or a tails, But if I toss 1,000,000 coins, chances are that 50% of these coin flips would be heads and the remaining would be tails. So this is called the law of large numbers. But people think that this can actually be extrapolated to, small samples as well. So for example, they think that if you toss 10 coins, approximately 5 of them would be heads and 5 of them would be tails. In fact, it's not very accurate to extrapolate the law of large numbers to small samples. As an example, I'm going to show you some figures. So these two figures are actually showing a series of tosses in which a vertical bar shows heads and a horizontal dash shows tails. So if you see, this is a relatively small sample. And I'm going to ask you which one of this is actually the result of a coin toss and which one is not an example of a coin toss. Many people would actually be selecting the left answer because it matches their intuition of randomness. They think that randomness means homogeneity, that even in small samples, you would have approximately equal numbers of heads and tails, and they would be nicely following each other. Heads के बहुत ज़्यादा एक लंबी streak नहीं आएगी, tails की एक बहुत ज़्यादा लंबी streak नहीं आएगी. If you have 3 heads, chances that you would be following this with the tails. In fact, इससे related एक fallacy, इसको हम Gamler's fallacy कहते हैं. And this relates to the normal law of averages, जो आम तौर पे non-statisticians talk about. They say that, okay, if we have won 5 tosses, we are now going to lose the next one. हालांकि हर टॉस पे the probability is the same and the future is not bound by the past. So अगर 5 heads आ गए हैं, still the probability of the next coin toss to be a heads is still 50%. But people actually think that because a streak has happened, now the time for a change has come. So इस case में many people opt for the left answer, but the real answer is the right figure. And people generally are put off because of the presence of large streaks, because they think that even in small samples, you would be having the long-term average scenario, but that is not quite the case. So I'll now be telling you कि ये असल में figures बनाए कैसे गए थे. तो जो left वाला figure है, इसमें हर tick mark जो है is the same as the tick mark on its left with the probability of 1/4. जिसका मतलब ये है कि इस किस्म का algorithm जो है, it forces that you will not have a very long streak. लेकिन when you have the probability set as the probability of a fair coin, you would have the sequence which is shown on the right hand side, and if you observe, there are many streaks. तो बहुत सारे आपको horizontal dashes नजर आ रहे हैं, बहुत सारे आपको vertical dashes एक साथ नजर आ रहे हैं, and this does not actually match intuition of people. And because our intuition is not in tune with reality, this actually forces us to make many logical errors. तो ये एक cognitive bias है, and because now this has been mentioned, we must take care that we, when we are talking of questions of probability, we use formal tools and we do not just depend on our intuition. Lastly, as an example of a cognitive bias, I'm going to tell you about the representative heuristic or the stereotyping bias. So humans generally, they form stereotypes of people, and then they make reasoning and decisions based on this stereotype. As an example, I'm going to provide you, an example from the research of Kahneman and Tversky, and this example states that, this was given to many people, and I'm going to tell you what they answered. So the example is, Linda is 31 years old, single, outspoken, and very bright. She majored in philosophy. As a student, she was deeply concerned with issues of discrimination and social justice, and also participated in anti-nuclear demonstrations. So then the people were asked, what is more probable, that Linda is a bank teller or Linda is a bank teller and is active in the feminist movement? चूंकि जो description दी गई है, that is actually leading people to the stereotype of a feminist, many people actually chose the second answer, which is the wrong answer. And that follows from the simple mathematical concept that a more general event is going to have a higher probability and a more specific event will be having a lower probability. So if you see, बैंक टेलर्स जो है वो एक बड़ी पॉपुलेशन है और जो फेमिनिस्ट बैंक टेलर्स हैं दे आर जस्ट अ स्पेसिफिक सैंपल ऑफ दैट पॉपुलेशन. तो जो बड़ी पॉपुलेशन है इनफैक्ट उसकी प्रोबेबिलिटी ज़्यादा होनी चाहिए, बट मेनी पीपल बिकॉज ऑफ द स्टीरियोटाइप दे टेंड टू चूज द सेकेंड आंसर which is not the correct answer. So in all the cases we've studied for the cognitive biases, आपने देखा होगा कि these biases are concerned with the human intuition and probability. और हमने देखा कि they usually do not, match very closely. So another reason that we should study formal tools of network performance evaluation, and we should not be banking just on our gut feeling and our intuition. Because in matters of applied probability, we would see that our intuition can fail us. So with this, I wrap up our discussion on cognitive biases. Our discussion focused on our human failings which force us to make irrational decisions. With this knowledge, it is hoped that we will be avoiding such errors and we would be aware of such biases so that with this self-awareness, we can avoid the logical errors which result from it. So let us now start our discussion about systematic NPE errors. In systematic NPE errors, we make some systematic error in one of the stages of the evaluation. So it may be an error during modeling, it may be an error of analysis, it may be an error of experimental design. So we're going to cover each one of these stages separately. The first thing we're going to talk about is about goals. So the first problem that we may have is that we have not set any specific goals, because all network performance evaluation is goal specific. So if you have not specified your goal, you will not be able to make any conclusions, because network performance evaluation cannot be done in the general case, because your choice of your performance model and the performance metrics are going to actually indicate the result that you're going to get. So it's important that we define कि ये जो सारी network performance evaluation हो रही है ये किस लिए हो रही है. Is it because we want to procure a system, or we want to design a system, or we want to analyze a system so that we can expand it later? So it's important that we set the goals. The other major problem which is related to goals is that our goals may be biased, and that actually leads to bad science and leads to bad network performance evaluation. So if our goal is just to prove that our system is better, we will always choose a performance metric and a performance technique that makes us look good. But that is not the real goal of network performance evaluation. Sadly, most network performance evaluation is done with biased goals, and that actually impedes the progress of science. So if you really want to do network performance evaluation, it should be in an unbiased, objective manner. So moving on from the errors related to goals to errors related to modeling, the first error that we can make is that we can choose a modeling technique which is not really specific to our goals, but it is, it follows from our experience with certain tools. So for example, someone who is conversant with mathematical modeling, if he chooses an analytical model, if that does not apply to the problem at hand, maybe an approximation is not quite valid. You have a very complex system and you cannot mathematically model it without making very unjustified assumptions. The second thing could be that a programmer would always choose a simulation technique, even if you can do the same analysis in a very short time using a mathematical model. Especially if we're concerning ourselves with very simple models, then we don't need to do simulations, and simulations typically take a very long time. So whatever our goal is, we have to choose the modeling technique accordingly. The next problem that we can have is that our model may be inappropriately detailed, which may mean too detailed or it may be very less detailed. So typically when we're doing simulation, we can arbitrarily increase the details of our model. So if we want to make a model very complex, we can do that. But generally it is not advised to have a very complex model, because if you have a complex model, it becomes intractable and it is difficult to gain insights from it. क्योंकि modeling का original मकसद ही ये था कि आप उसको approximate करें, because then it is easy to understand from that simple model. But if we simplify too much and remove too many detail, then it does not actually reflect reality. So we have to, find a very delicate balance between these two, conflicting goals. Another thing that is going to affect your results a lot is the kind of workload that you perform your testing on. And in fact, if you choose a wrong workload का मतलब है कि आप नेटवर्क परफॉर्मेंस एवेल्युएशन कर रहे हैं, तो आप क्या अज्यूम करें कि लेट्स से रिक्वेस्ट कैसी आ रही है, तो अगर आप वो चेंज कर दें या आप ऐसा वर्कलोड अज्यूम कर रहे हैं which is not practical, then this is going to lead you to a result which is not valid, and it may actually give you conclusions which are even misleading. So another thing is that we assume our model and our workload to be static, whereas nothing remains static in the real world, everything changes. So a workload, especially of computer networks, is evolving at a very fast pace. So we have to actually take cognizance of this fact and also make our model such that we are able to actually change it when the actual workload has changed. So another thing is that we make inappropriate metric choices, which means we may only select those metrics which makes our system look good. But for actual NPE study, we need to study all the metrics which are relevant to the system at hand. So another area of NPE in which commonly errors are done is experimental design. And that would be that you are conducting an experiment and ignoring certain very important factors. So you're not even considering those factors, but that factor actually has a lot of effect on the performance of the network system that you're considering. It may be because of reasons of simplicity, or it may be even due to ignorance that you don't know that this factor is so important. But it is very important that we find firstly all the factors which are relevant, and then we model them in our experiment so that all the confounding variables are taken care of when we are establishing relationships. So this is very important. Another important factor is analysis. और analysis में अक्सर network performance evaluation studies go wrong, because it may be that you're not doing any analysis. This is also done. Many people just take measurements and they don't do any analysis on that. So just measurement or creating data is not enough. You need to also do some analysis and gain some insight from it. Another problem could be that you do premature analysis. Your model is not yet completed, but you just based on an approximate model, you haven't done your modeling in a complete sense, but you in a premature fashion start analyzing that. So it may give you numbers, but those numbers may not be conveying any meaning. Another thing could be that you do not do any sensitivity analysis. Whenever you're presenting results, those results may be depending on certain factors. अगर वो आपकी जो assumptions हम change कर दें, it may be that your results would completely change. So when you're presenting results, जब आप अपने measurements को analyze करते हैं, it's important to share कि okay, we use these assumptions, but if we do not have these assumptions, our results would change, but they would change in this manner. Lastly, it's very important that we do not, hastily generalize from observations. We must use the tools of statistics to draw conclusions. So all measurements have errors, so we have to be very careful here. हम जब भी कोई measurement present करें, we must necessarily also give the amount of uncertainty in that data. And lastly, one of the major cause of failure of network performance evaluation studies is the lack of usage of the scientific method. So we've already motivated that scientific method helps us to make objective decisions about performance issues. So it's important that we use network performance evaluation. We do that in a scientific way. And when we talk of drawing scientific conclusions, it's important that we do not use anecdotal evidence. So network performance evaluation has to be done objectively in a dispassionate manner. It cannot be done on personal anecdotes. So these are some common issues in doing network performance evaluation studies. We've covered issues relating to design of experiments. We've covered issues related to analysis and relating to modeling. So it's important that we take care of all these issues. And the general idea of this lecture was to relate all these errors so that we may be able to avoid them in our own studies. So with this, I'd like to wrap up our discussion by giving you a few concluding remarks. The first remark I'd like to make is about logical fallacies, and I'd be saying that it's important that we further research on this area so that whenever we're making arguments, our conclusions must follow in sequence from the premises. Also, we talked of cognitive biases, and we mentioned that it's important to know these because they exist in us. So if we are aware of them, we can counter their effects. And lastly, we also mentioned some common NPE errors, and we mentioned that after learning them, we should take every care to avoid them. So with this, I wrap up today's discussion. I'll see you next time, inshallah. Assalamu alaikum.